kilometers. We used to say 19 by 15. And we've identified what we think is the Goldilocks site in Spring Valley, Nevada. We've started to engage with the local authorities about the permitting process, and that's advancing quite nicely. It's going to operate over a frequency of 0.7 to 2 gigahertz, and the spatial resolution, for those with good memories, it's been tweaked slightly, so that's also related to the array extent. And again, highly optimized for surveys. So we are aiming to start construction next year. That's permits willing, and then get to first light around 2028, and the surveys would then run in the 5 years subsequent to that. So roughly 2029 to 2034. So on the site, Spring Valley is a fantastic site. It's surrounded by mountains in almost all directions. There are very few cell towers there. So the plot at the bottom, you can see the RFI comparison to the Ovro site. So Ovro used to be a fantastic site. The communities around there have grown, and they brought their phones and their computers with them. But the Spring Valley site is still like I think Ovro was when that was established. So that's pretty positive. In addition, in Spring Valley, there is a road up the western side, so it's accessible. And there's a power line next to the road. Unfortunately, the power available on that power line is a little bit limited, but at least there's something there. So there's this blend of infrastructure and radio quietness that I think is very rare anywhere in the world. And we can use the nearby town of Ely as a base. And also that the soil is actually very conducive to the kinds of construction that we aim to use. And that is what it looks like from a drone. So hopefully sometime soon there'll be 1,650 antennas in this picture. But you can see that the valley is actually quite flat. The floor was once a lake bed, clearly, and it's surrounded by the mountains you see towards the horizon. So a near ideal site for a radio telescope of this size. If you want to go larger, you're going to hit the mountains, and that start to become more challenging. Right, so into system design, and I'll splash up another slide that you won't be able to read, but just to show you that we have a product breakdown structure. And I will address that by going to this also slightly confusing slide, which is a block diagram trying to show the different aspects of it. So this block diagram reads from right to left, and on the right-hand side, you have the antennas, so 1,650 spread out all over the valley. Each antenna powered by a small solar power station. So close to every antenna, there'll be a small array of solar panels and a battery. And the signals are transmitted back in analog form to a central building close to the array. And the fiber path is constrained to a maximum of 20 kilometers. So that's our range. Then once it hits this central building here, the fiber signals are converted back to electrical, and then it goes into the channelization. So the channelization is done on FPGA, and that's in the valley. And that's partly to reduce the data rate, because from there, we ship that back via a 50 terabits per second link to the town of Ely. Now, Ely is conveniently located on the other side of the mountain, so there's nice RFI shielding between the two. So this small little building needs to be shielded, but the big, well, maybe not so big, I'll get to that, building that's in Ely, that's just a normal building in an industrial area in a town. So inside this facility in Ely, all of the processing happens, and then from there, there's a gateway to the outside world where the archive will be. We also have, in this block diagram to the left, you'll see remote operators, but I'll point to Vanessa's talk, which is a couple of talks down the line. because we're not planning to have remote operators, and Vanessa will explain what that means. So construction, we've got to do two things. We have to install the antenna pedestals, and we have to plow in the fiber. So this is a plow that shows how that happens. And in sandy soil, it goes really well. If it gets rockier, it gets a little bit harder, but it's pretty quick. And this is the way that telecoms companies install fiber when they do it next to the roads. This is actually how we came across this company. They were installing fiber next to Overo. And so I think Greg Hallinan went to them and said, hey, how do you do this? And that was a key enabling factor here, because the cost of doing that went from many, many millions to just a sort of a manageable number of millions. And then in the middle, you can see what happens to that beautiful ellipse we had on the first image when we first saw the valley. It hits reality. So there are things in the valley that we have to avoid. Some of them, you can clearly see which are the man-made ones. So some of them are private properties. So there are a couple of rectangular shaped things that are cut out. Some of them are mountains. So towards the southeast, you can see that we've avoided the worst of the mountains for two reasons. The slopes start to become problematic, but it also gets rocky. And so this construction method, of course, wouldn't work there. And then there are some circles, and the circles are places that we need to avoid because there are sage grouse there. So sage grouse is a sensitive species, and there's a comprehensive program in the US to prevent them from becoming endangered. And so we have to avoid their habitat as much as we possibly can. And the QR code on the left is a link to the ArcGIS site where you can actually see all of this information. So the central picture is effectively a screenshot of that. And you can zoom in, you'll see the antenna locations are little dots, the fiber lines connecting them all. And all of those fiber lines then go towards the west to that point where our buildings will be, and we'll convert that back to electrical and do the channelization. That also happens to be right next to the road, which goes up the west, and right next to the power line up in the west. So those are all very handy things to have. Then back to low noise amplifiers. So if you watched carefully on the previous picture of the low noise amplifier, you would have seen a very simple matching structure. And we looked at that again and thought, we've left some kelvins on the table here. And so Kieran Sheila, for their PhD, did an optimization technique for the matching circuit that resulted in this very funky looking matching network. So that's a very nice result. But of course, it wouldn't make a difference if it didn't improve things. And so the black line is Kieran's noise temperature, and the red line is the old one. We think that there's probably some scope for additional improvement around here, but that's still a work in progress. Then after the low noise amplifier, signals go into the fiber transmission system. So pictures of the transmitter and receiver. That's fairly straightforward. Of course, the fiber path has a dynamic range limitation, but the dynamic range of the fiber link at this stage is very close to the dynamic range of the analog to digital converter. So there's not all that much more to have here. And then it goes into processing. So this is an overall processing diagram, and the dashed red line is the split between what happens in Spring Valley and what happens in the Ely processing facility. So on the left, analog to digital conversion and channelization. Then you have this 50 terabits per second link that runs approximately 100 kilometers back to Ely. And then after that, in our processing, it's all GPU. So the rest of the processing on the same node would perform the correlation and the imaging. So you gain a lot by not having to move data around too much. And I think that's really a key enabler to the radio camera. And so if you look at the plans for the buildings, you'll see a few buildings there. The big red one is a temporary facility where we'll do antenna assembly. And at some point that disappears, and you're left with 4 smaller buildings. 2 of them are just storage and shelters for the people working there. The other 2 will contain the FPGA-based channelizer systems organized in racks that might look something like that, with some UPS and networking, and obviously fiber management coming in. And then it goes on to fiber. So this is the backhaul fiber route. Of this, about half is existing dark fiber, or existing or coming dark fiber that we could just pay people money to get access to. The other half, the half that goes from the north in Spring Valley down to the south here, next to Highway 50, we have to install ourselves. So that's a new build. And then we get to processing, and here I kind of want to, I'm not going to give you all the processing details today. There's another talk on Friday where there'll be more on that. But I do want to break off and give you my summary of NVIDIA's GTC 25, which I think is significant in our community. And so what we became aware of are these big rack-based systems that are geared towards AI applications. They have, at the moment, there's an NVL 72 system. There's an upgrade to that coming, and then an NVL 144, which will use the Vera Rubin processor GPU combination. And beyond that, Rubin Ultra, which goes to absolutely insane numbers. And what's important here, and I've had to base this on publicly available information. So you'll note that the FP16 and beyond, I'm not saying anything about. NVIDIA obviously know that, so you could ask them and they can tell you. But if you look at these numbers, these are exaflops. This is one rack, and you get 1.2 exaflop. Yes, sure, at FBA, but you can scale that to the higher bit depth numbers. In addition, it has insane bandwidth internal to the rack. So 130 terabytes per second, 14 terabytes per second coming in from the outside world. So that is, more than enough. And then from CPU to GPU, also very wide bandwidth. I will note, I adjusted NVIDIA's numbers. NVIDIA quote bandwidths as up and downstream, and they add them together. This is one direction, so this is more meaningful to me, but probably not to the marketing people. And so these racks are available, and if we project our processing requirement onto these racks, we go from an estimate in what I'm about to show you would represent in our previous design 40 to 50 racks of equipment, and now it's 4 racks. And these are standard size racks. They're not standard racks because they're all liquid cooled and the power density is pretty high, but it's a factor of 10 in floor space. It's at least a factor of 3 reduction in power. So this is a big issue. Anyone building a big instrument, you should be paying attention to this. Then progress. Where are we right now? So at the Owens Valley, we've built a test array, and this is what it looks like. And I'm not going to say too much about it because Benan's going to speak right after me, and he'll tell you more about the results of the test array. But I do want to add something that he's not going to speak about is the minimum viable product. So from a software perspective, we've created this minimum viable product, which is just an end-to-end, very limited integration, testing all the interfaces, getting everything integrated, getting up and running. That's running now, so we can control antennas in that array using what are the early prototypes of the software systems. And it becomes a development bed for that. And ultimately, it transitions actually to a staging platform where we can test software before we deploy it to the production array. So it has several lives. And initial testing has started. 2 of those antennas are solar powered, and the others are grid powered. And there's a total of 10 of them. 9 are close together, which you saw in the picture. 1 is about 1 kilometer away. So we can connect them. At this stage, we have signal processing for 2 antennas only. We can mix and match and plug in whatever we need. But by approximately November this year, we'll be able to process all 10 of them. And then another test, so that's in Owens Valley. And Owens Valley, as I showed you on the early slide, is from an RFI perspective challenging. So we've also started to do testing in Spring Valley. In Spring Valley, we can't touch the ground yet. So we can't install an antenna. But what we can do is speak to the owners of those private properties and say, can we park a trailer on your property for a little while? So this is an antenna that's mounted on a trailer. It can be manually tilted, but it's not steerable at all. So it's mostly used to just point up at the sky and get some in situ measurements of the environment in Spring Valley. And again, I won't say too much about it, but we can do some preliminary TSIS measurements, and it looks like we're at about 23 Kelvin today. So this, again, for uncooled receivers, we're pretty happy with where we are, but we're not stopping. We're still doing some work to eke out every possible Kelvin. And with that, I will go to questions and acknowledge all of our partners on this slide. We've had tremendous help from Schmidt Sciences to get us to where we are, and all of these other partners are involved in some way. Thank you.
The power system for the antennas. You need to worry about the RFI probably inverters there. You probably
Absolutely, yeah. So the solar power, it needs to be designed carefully, and there are all sorts of lessons. In fact, from the SKA, there are lessons that are applicable here because there's solar power in some of the SKA remote stations. But yes, we absolutely have to worry about that. It's possible, because our power requirement is so small per antenna, it's possible that we would run with higher voltage batteries and higher voltage panels and just forego the efficiency. So there are options there, but yes, it's something that we are working on actively.
Really interesting. So I think it was in Japan a couple of years ago at URSI, there was a talk on DC2000, and at that point the configuration and things hadn't met reality yet. And it was a very interesting talk because the combination of clever tweaking of the proposed antenna positions and clever weighting of the data and the visibilities was one of the things that gave the radio camera really, really good properties. It was really impressive. So I'm just wondering how that has changed or had to be modified now that you're facing reality.
Yeah, so we completely changed the array layout based on a new optimization technique, given the ground truth of what we needed to avoid. So there is the shape, but inside that shape there are water features and cultural sites and roads. So we have shape files of all the layers that we need to avoid, and all of that goes into an optimization that was run to get to this. And that optimization was trying to achieve the same performance as we had in Japan. And it actually recovers that performance quite well. We did allow the array to get slightly larger. So we had a few bands where we said, okay, this area is not, there's nothing sensitive here, and it's construction-wise, it's easy to construct. So let's extend that, and ran that. We had that in bands, getting larger and larger, which obviously gets more and more expensive. And we found that we had to add one band only. It's a 500-meter band. So that changes the shape a little bit, but that got us back to the same performance.
The radio camera philosophy is a little bit different from like the classical way, classical radiometer might handle data. I'm just wondering, the calibration strategy for the DSA2000, is it different from an instrument like, say, MCAT or SKNet or something? And how is that integrated into the radio camera pipeline?
Yeah, I mean, it is different. We actually use a lot of forward modeling to establish that and to validate the algorithms. But those algorithms are being developed, and there's a lot of online calibration happening. So yes, it is. It has necessary differences. And then in the imaging pipeline, the output of the radio camera effectively are images, but there is still at the image level, there's still deconvolution that happens. So yeah, it differs in subtle but important ways, pretty much all the way through the pipeline. All right. One more, and then we have to move on. Otherwise, the session chair is going to beat me up.
Those of your imaging, you need high quality images without a lot of computer processing. But a limitation often in these cheaper antennas, which you require to budget, the pointing accuracy of the antennas has a fairly significant effect on dynamic range. So how are you doing on that specification?
So the specification on the antenna for both pointing and surface accuracy is actually that of a much higher frequency antenna for that reason. So so something's got to give. So we've had to include a tighter specification in order to achieve that. Yes. All right. Thanks, speaker, again. And then next up, we have Venant, who's going to tell us more about the test array.
I am.
Those speakers there.
Yeah.
We'll have to use that.
Yeah.
Just pointer for you.
So how do you have the pointer going up?
You have to point. Yeah.
Up. When you move your screen.
No. You don't do that. Because that's not part of it.
Wow, we're spending. Thank you, Francois. So he gave you this kind of general idea of what DSA 2000 is and what we're doing and where we're going and what's happening. What I'm going to be doing is going to give you a very focused overview on the test array that we're building for DSA 2000. All right, sorry. Anyway, DSA 2000 in a nutshell, I think Francois already covered this in his slides, but I'll go through it again. So it's 1,650 antennas, 6.15 meters size dishes. It's going to be spread in an area of 20 kilometers by 16 kilometers. Frequency range 700 megahertz to 2 gigahertz, and it's highly optimized for service. We are planning on starting construction in 2026. First slide 2028, and it's going to run for 5 years for the key surveys. So this aggressive timeline itself should tell you why we need the test array. So we have 9 antennas in a tight cluster, 45 meters by 20 meters. And there's one which is a kilometer away. And the one which is the long kind of baseline one was the first one, and it was the prototype. And this was a selected site for this cluster of antennas. In this one, we have 5 of the 10 are overall design, purely overall design. 2 of them are by a company called MTEX, and the rest of the 2 are overall design, but manufactured by MTEX because we wanted to see if they could build our design at a cheaper cost, given their production line and their manufacturing practices. So MTEX antennas, they're controlled by their own web interface, and they use an MQTT protocol to talk to the antennas. 3 of the antennas have complete end-to-end signal chain. 2 of them are fully functional right now, which is what we are using, and those are the MTEX antennas. Vikram and I and one of his students, we've been taking data for a few weeks now, I should say a few months at this point. So the overall MINEX antennas have their controller system being built and tested right now on one of the antennas. It's not safe to run them the way that they are right now. which is why we're giving them a little bit more time before we start working on them. So Francois gave the timeline of November, and this is the timeline that we are giving ourselves for those antennas to come online, and then the actual design for the digital backend is going to come to overall, and then we're going to integrate all of that together. So like I said, we have two designs. One of them, Ovrominex, in-house design. The other one is by the MTEX company. So the dishes in-house were hydroform. We have a hydroform on site. Those are actually 5-meter dishes. The actual DS8000 design is for a 6.15, but the 5-meter was for a previous design that we've changed now. But since we have them, that's what we are using. The MTEX dishes, they were foam pressed and glued together. They're made of petals. It's not one complete. It's not like a dish that's, yeah. Again, anyway, it's just petals glued together and foam pressed. A few differences between those two antennas. So the turn head for the MTEX are way more complex than the overall design. They handle backlash a little bit differently. They have an additional motor for that. We have a magnetic brake system that does it differently. The fiber wrap for the overall antennas, they go through the pedestal. There's no wrap system. It's just a fiber cable that hangs, and that's it. The MTEX, it's outside of the antennas. They're doing a redesign right now. I'm not too quite sure what they're gonna come out with. So we'll see in the next few weeks what they say about that. We kind of did a hack for the digital backend just because we need to get data out as quickly as we can. So we chose to start using the RF SOC 4x2. So this one is actually the code has already been written. It has a full correlator running on it. So each of these RF SOC can handle 4 inputs. So this one right now is handling 2 antennas, the MTEX ones, and it's built to handle a frequency range of DC to 2.4 gig. It spews out 8,195 channels at a frequency resolution of 293 kilohertz. We are integrating at 3.5 seconds. We could tweak that. It's just what we are using right now. We're kind of limited because the server that we're using is not a high performance one. Well, kind of high performance, but we can't store too much, and the data throughput is a little bit too much for it. But anyway, in the next few weeks, we are thinking of migrating everything to a higher performance server, and we're gonna be getting the actual RF SOC prototype coming on to the site, and this is gonna be replaced by that. And one of them is actually gonna go to Spring Valley for interferometer tests, which I'm going to talk about later. So the test area has an extension, and that's the antenna that Francois was talking about. This one right now is a standalone system. It's just one antenna that we wanted to get out to the valley as fast as we can, just because of the RFI environment that we have on site is not great, and we wanted to do a little bit more in terms of measurements, and especially the sensitivity measurements that I don't think we can pull off at overall. But anyway, we have a team that has gone out there, and they've already used it for system temperature and for RFI measurement. I think pretty soon we'll have a second antenna that's going to go out, and that's going to become a single baseline interferometer, and which we are really excited about. That the design for that is actually ongoing right now. So we have done what we call an early performance assessment on the system that we have right now. So it's been divided between hardware and RF tests. I'm going to start with the hardware stuff that we've done. Like I said, the fiber wrap that we have is basically just a cable that hangs inside the pedestal, right? So what we've done is we've hung one of those fibers, and then we've twisted it back and forth, and then we measured how the signal degrades with each rotation. And the blue curve is basically the corrected one, and that shows that there's not much of a change. It stays quite stable, which is quite nice, and which is quite it was a relief for us that this is working. We've also done like temperature measurements tests on the dishes. So we put sensors on the back, on the feed legs, on the counterweights, front of the dish, just to see how the gradient changes over day and overnight. And as you can see on the plot on the right, that the gradient just during the day can be quite bad. And this is kind of informing us on what we're gonna do with those dishes. Are we gonna paint them? Are we gonna sandblast them? What are we gonna do with them? Right now, painting seems to be the best option, and we wanna try and get to the best solution for this, because the pointing during the day or early night can be really problematic if we don't correct for this. So we've also done some extensive, we do metrology tests on all of the dishes that come out of the hydroformer at Ovro. This is 2 of them. It's quite impressive that we get a 0.5 RMS surface accuracy on one of them, and the other one is 0.6 something. And the repeatability RMS between the dishes is almost 0.2 RMS, which is quite frankly amazing. Some RF tests and some kind of instrument characterization. This is a delay spectra that I took a few weeks ago. We saw standing waves on the system. We saw standing waves between the dish and the feed, and we were kind of wondering where is that coming from. And we took some autocorrelation data, and I did reverse FFT on that, and this is what came out of it. We see that what we have right now does produce a little bit of standing waves, and we are looking at how to mitigate that right now. Whether at the base of the dish we put a cone that alleviates some of the standing waves, whether we improve the matching between the cable and the LNA, that's TBD. But this is the kind of test that we're doing on the system right now. Like I said, it's very early, kind of early commissioning test, whatever you call it. But yeah, this is just to give you an overview where we're going with this. This one is the sensitivity test that we did, Y factor test that we did in Spring Valley. We were able to get a TC of 23 Kelvin in the quiet parts of the barn. If you look between like 1.6 to 2 or 1.6 to 1.8 and 1.35 to like 1.4. This is where we kind of measured the Y factor, and we got that thesis. So purely RF, we started looking at like characterizing the system end to end, and we start by taking autocorrelation data, and we're looking at the spectra as we go, and we are playing with filters on the front end just to see how we eliminate harmonics in the LNA. We're playing with attenuation settings. We're playing with FFT shifts. We're doing all that kind of stuff. And this is one of the plots that we took after doing a bunch of kind of, a bunch of messing around, I should say, and it kind of looks good now. So this is why I'm showing it. All right, so this is a drift scan that we took of Cassiopeia a couple of nights ago. The really dark bands, that's just RFI. And then you can see it goes from kind of faint to bright, and which is where you kind of see Cassiopeia get into our beam. This is kind of a nice plot to show. We also done some pointy scans, again, using Cassiopeia on and off. And we've done that on the autocorrelation spectra. We also took some cross correlation spectra, and this is a work that's ongoing right now. And we've done a lot of optical pointing And right now what we're doing is we are working on the radio pointing side of things. I have a talk on Thursday where we talk about the pointing and the tracking of the MTEX dishes and some of the over ones. What else do I have? Yeah, so finally, this is one of the nice ones. We have been taking data for like I said for a few nights, and one of the things that we were pushing for is to do these things like looking at H1 or in this case OH, and that's because one of the best ways to find flaws in the system is actually push it as much as we can and do these things and try and characterize it so that we can do these, I wouldn't say little science, but science. And this is a detection of OH that we got a little while back. And I also wanted to mention the RFI measurements that we did in the valley. And this is the plot of all the sites that we hit in the valley. And we have like almost, I don't know, almost 20 of them. So we went around the site and we took measurements for an hour, 2 hours, 15 minutes, you name it. And as you can see, most, if not all the sites are pretty clean. Like the orange plot is the Spring Valley site and the blue plot is the Ovro site. And you can see that when you take a median plot of these results, this is what you get. So it is quite quiet. Okay, I'm gonna finish with this. So this is what we've done, and this is where we wanna go after. So the tester being an engineering kind of test bed right now, we wanna move to it becoming this kind of pre-commissioning instrument, and then finally getting transitioning to a full commissioning again instrument. But we want to build the capabilities of doing that by starting with this. So some of the things that we want to do, we won't be able to do it at Ovro just because of RFI, which is one of the reasons why we're pushing for having a fully functional system in Spring Valley. So we want to look at stuff like, doing long integration times, root out systematics. We want to do like closure phases, closure visibilities. We want to do some pulsar timing measurements out there. We want to look at some quality of the visibilities by doing RFI characterization and RFI flagging and mitigation. Doppler tracking. I mean, some of this stuff is like pretty standard. So we want to start with that and then go from there. I think this is it. And thank you for your time. Any questions?
Yeah, why you ask me? I'll hold it up with a question like this.
Hey, cool. The system temperature plot, is that OVRO or Spring Valley?
Spring Valley.
So, kind of, I see these RFI-free plots for Spring Valley.
Yeah.
And the system temperature is quite noisy.
Yeah.
What's that?
So that's because that's on private land. So that it's just on the side of the road, and those sites are gonna have RFI on them. So the plots that I showed you, they are like in the valley, and they are the actual sites where the antenna is gonna be located. That one is not gonna, yeah.
Just continuing on. Sorry. Just continuing on for dealing with heat. You said that you were like some of the ideas that you have would like paint them. What do you mean like paint them? Is it like, do you mean like just like painting them with paintbrush, or do you mean actually like having like some sort of specialized paint material that you utilize when?
So we have this kind of white, cool paints that we are looking at, and one of them has been painted with it. and we're taking measurements, like temperature sensor measurements out of it, and it's looking pretty good.
Or
No,
nothing?
no, it's just for diffusing the solar heat out from the feed.
Another question.
Yep.
So you said that you had essentially two different companies making these stuff. Well, you had one company making one, another company making
Yep.
another, and then making the other design. Is there any possible? Have you observed any problems with the different designs of the companies, or is there some differences in the measurements of the companies? So they, are there any sort of little? I guess what I'm just saying is that is there any noticeable measurement differences between the designs and the manufacturing? The manufactured telescope of the companies at all.
I mean, the German company MTEX, they are a company made for these things. Like they build dishes for their living, right? Ovro does not have a production capability, right? Doesn't have a production line, doesn't have any of that stuff. What we've done is we've designed one dish with the hydroformer on site, right? I don't know if that's where you're going, but in terms of manufacturing practices, those are two very different things. We will have to build our own production line on site if we go with the Ovro design, but the baseline design right now is the MTEX antenna, which is why we're focusing our efforts in commissioning it and doing acceptance testing on it.
Like more likely like the calibration of each of the different designs. We have to change them up a little bit to try and match each other, or is it just measurements there?
No, we're only gonna use one of them, right?
Oh, this is just for testing.
This is just because, see, we start with the baseline at Ovro, and then we said, okay, we need to have not a competition. We want to see if another company or somebody else can do it better at a cheaper cost. And this is where MTEX came in.
Okay, so you're not using both.
No, we're not going to use both. It's only going to be one, yeah.
We'll add to that. So as Ron alluded to earlier, the performance of the antenna is critical. So we not only have a surface accuracy spec, but we have an antenna to antenna accuracy spec, which is even tighter. So they've got to be very repeatable. So they all go through. So the mix and match idea wouldn't. On your experiment, showing the phase variation with fiber flexion. You mentioned the corrected curve. I was just wondering if you could go into detail of the correction.
Oh, you have to talk to James Tam about that. I can't quite remember what he did there. But I can send you the link to his paper if you want, which will make it easier.
So I think it's temperature, right?
Oh yeah.
Temperature change to the measurements.
Yeah, he had the doors open in the hangar when he was doing that. So the temperature was varying quite a lot between measurements, and this is why you saw this variation. Yeah, thank you for that. Yeah, so he corrected for the temperature differences, and this is when he got it to flatline.
Thanks, Jan. I thought the deals would be slightly over time. So good history. Thanks again.
And then next up, and to close off the session today, yep.
You should have received even what they don't have it, but Pedro.
Yes.
That's how we will have come.
Oh, is he going to come today? Oh, okay, great. So yeah, so we'll have Pedro presenting his talk from this morning that he missed, and great to see you.
All right, so over to Vanessa.
Cool. Thank you. And thank you for the opportunity to present, everyone, and thank you for making it to 5 p.m. on day 2. I know it's a really long day, so I'm looking forward to going into what I guess is a slightly different perspective. So over the course of today, we've seen a lot of different interesting upgrades, and I think, I mean, URSI as well, but also one thing that is also really clear in radio astronomy is that we often are driven by innovative engineering. So if you look back at the course of the talks today, new hardware upgrades, instrumentation, creative approaches, technologies. And I guess I'm here to make the case that as well as all of that, and as well as the key discoveries that will be made, one of the key things we also need to do is thinking about the rise of automation. I put AI there with a star because we'll come back to that. It's not just about AI, but it's just the changes in the computing and the software environments that mean that if we really want to get the best outcomes from the new instruments we plan to build, then we have to consider the holistic picture of how we're going to operate them and the ways we can do that differently. I started with this because it's a long day and like I'm almost asleep because this is such a radical like time shift for me. But this is my peak hour if you don't get up really early. So the reason I'm starting with this is we'll come back to it. But suitable context, so it's not everything. There's a slide later that'll go into this in more detail. But there are contexts where considering autonomous and automation make more sense, and there are contexts where you can say, all right, well, it doesn't make as much sense. And in terms of some of the innovations, and I've put stars in both of these because these are not complete. So there's a lot more to consider here, but these are the examples I'm sort of going to explore as part of this talk. And here's another slide where it's very much trying to capture some of the different things that have been happening, some of the things that have been happening for decades, by the way. Spike goes back to 1990s. I didn't know that. But so there's a lot of different innovations happening in radio astronomy, in other fields, beyond astronomy, that are really showing the examples of the benefits of why we need to shift to more and more automated or autonomous approaches for the way we do things. So like I said, this is not complete. And actually, I know everyone here is going to know of different things that are not on this list. So please find me over the course of this week and tell me about the ones you know. Most places have not yet gone fully autonomous in in the full workflow. It's starting with different pieces. And so I obviously am closer to the scheduling side because that's where I focus. So I'm really interested to hear all kinds of both scheduling and other approaches you know of. I wanted to show this. So ATNF didn't actually exist way back to Dover Heights. But if we think about the evolution of observatories over time, what we've seen is we started with very highly manual processes, specialists, small teams, and then it became more PI driven, more organized, but still teams doing the work, a lot of hands-on observing at telescopes, more schedule driven, more semi-automatic. Then as we get further on, we start to see more automation, remote triggering, reactive triggers, until the point where we get to a lot of the instruments now, we're trying to answer really big questions, complex questions, lots of constraints. And so we need to go toward more automated and observatory-led kind of ways of running these facilities. So this is an example of ATNF, which is the Australia Telescope National Facility. This is run by CSIRO. But you can also apply this, and I checked with OVRO people that it's similar in other cases. So I'm sure there's each observatory has a similar sort of approach to this, that we start with quite hands-on, quite experimental stuff, but as we advance, we want to do bigger things. And so again, interested to know about the cases of observatories you're most familiar with. So what are the suitable contexts for this sort of autonomous operations? So in looking at the kind of cases we've been working with, both with ASCAP, with DSA and others, it really comes down to these sort of considerations. But again, if you can think of others, I'd like to hear, it's definitely not complete, but scale, larger scale is more likely. Remote, if you're remotely operating as opposed to hands-on, if you can't walk outside and just tinker, I mean, space telescopes are a good example also of the remote aspect, and rovers. Complexity, more complex instruments, more complex tasks to deliver on. Time scale, if it's going to last longer, then it's worth the investment of doing things in a more autonomous way. The teams, distributed teams around a country or teams around the world, as well as the nature. So is it something that has to be a little bit more production as opposed to experimental? But actually, I would say even in experimental cases, even in high-risk cases, you might save a lot of time, money, and resources if you think about the ways you can minimize reliance on human intervention. So this is just a list of some of the current and future facilities that this will apply to, and again, not exhaustive, so keen to hear of other cases where it's already happening or you're interested in it. So I'm going to cover 4 high-level case studies. I'll talk most about scheduling because that's the one I'm closest to, but try and touch on a few other cases as well. So the first one, autonomous scheduling. So in ASCAP, it's a high efficiency instrument, it has to deliver surveys at a high rate. It's also dedicated to surveys. So it's not, even though we do have the capacity for PI-driven projects. And if you want to hear more about ASCAP, I'm talking on Thursday morning, so I'll talk more in detail about ASCAP there. But it's really about surveys. We didn't have a history of the operator model. Ron and others could tell you more about why, but we didn't. So it meant there was an opportunity, even though we were committed from the beginning to remote offsite operations, we didn't have a rigid definition of what that science operations would look like. So this created an opportunity to explore alternatives. And so the one that I developed was Sauron, which is an autonomous scheduling approach. That paper needs to be written, and that's a this year thing maybe. So what Sauron stands for is scheduling autonomously under reactive observational needs. The idea was that scheduling was something that we could use as a starting point to look at ways to apply this broader across the ASCAP workflow, which is by nature quite automated from its initial conception. It was always going to be quite automated and not lots of humans doing things along the way. I put a star here because while we did have to do some degree of automation, we had to have a consolidation period to increase the automated control of the telescope and some of its robustness and stability. It didn't have to be perfect. And so that's one of the things I've heard sometimes is like, oh, we couldn't possibly automate until we stabilize the system enough. And, we need to start. And it's sort of true to some extent, but actually, if you wait till it's perfect, that's probably the end of the project. So I think there is a foundation that you need to meet, but it doesn't have to be perfectly everything stable all the time. And in fact, one of the ways that automation has helped us is to work around the ways it's not perfect. So that started originally in late 2020. It's been ongoing development since with new features depending on requirements. Ron reminded me that I hadn't said why autonomous scheduling is important. So this is just some of the examples. In our case, there's a lot of complex inputs. Every team wants something different. There's specifications, there's constraints. This team doesn't want to observe it in the day. This team doesn't want to observe between this angle on the sun. So there's balancing all of those different constraints. This team doesn't want to observe if ducting is present. So all of those different things become an input that is much easier for a machine to read and balance than it is for humans. Systematic and deterministic, that's a choice we make. We could choose to have something that is, more deep learning, less predictable, but we actually in this case wanted something that was low level, systematic, so that we knew exactly, given the same set of circumstances, it would make the same choice. So that helps with understanding what it's doing. 24/7 operation, we don't have to pay super to Sauron. We don't have to worry about overtime. So this increases our efficiency. And it means that that's one less thing, if other things aren't working, then it's one less thing we have to worry about if it's able to react to change and work essentially all the time. It also allows us to redirect human expertise. So this is one of the biggest, costliest parts of a project. If you can limit the ways in which humans have to do things at a certain time, then you can put that into other things like developing new features, debugging complex issues, controlling the system when there's a risk to it, that sort of stuff. And it's allowed us to develop new modes. So a couple of examples are Smart. Don't know, is Leroy? Yeah, hello. So if you want to learn more about Smart, but this is an RFI survey, and it was actually a really fun thing to think about how do we build this into Sauron to make sure that it tries to survey different parts of the sky at different elevations, different times to build up an efficient census. So that's the example there, as well as allowing us to build things like coronal mass ejection triggers so that if a trigger happens, then the team can send an alert and Sauron can react as soon as possible. So those sort of things, and a lot of reactive triggers exist across telescopes everywhere. So this is a plot of, to use this after all. This is a plot of kind of efficiency over time. You don't have to know the details, but every little kind of snippet there is when Sauron's been able to just do its thing without any interruptions, usually over shutdown periods. This part of the plot is more when we were doing pilot surveys, which were really important for us to build up operational confidence. But when we get into the real surveys, we need to be a much higher efficiency. And you can see we're kind of getting there. All of these interruptions have nothing to do with scheduling. They're to do with the times we can't schedule for various reasons. So if you look at that over the history of ASCAP, you can see generally the trend is good. And we're able to, in times where we can actually just run science operations without anything going, without any stoppages, we can hit very high operational averages, but our KPI is 70%. Go away. I also wanted to show an example of, and we'll come back to this briefly, but simulations versus predictions. So this is one of the challenging things that I think the science community has had to think about is like, okay, well, but when am I going to get my data? How is this going to play out in the long term? So this is a simulation. It's like weather. I actually think it's a lot like weather prediction, particularly if you want to be dynamic and reactive, you want to react to the conditions. So it's very hard to say anything the longer you go in advance, unless you're saying it at a high level. This was for a April shutdown, so we were basically able to observe without interruptions for a couple of weeks. That's the simulation of what we would do, and that's the reality. So on that kind of timescale, I can say with a lot of confidence, this is how it'll play out if nothing goes wrong. In this case, we had no weather interruptions and no downtime. So it was almost as close to an idleized system as you can get. So in those particular cases, but then there's a question of, okay, how do you extrapolate this 2 years at a time? And that's still a work in progress. And as Francois mentioned, we are collaborating with Caltech to extend this to the GSA 2000 Observational Planner, or OPL. The idea is to build on what we've learned from SORON and the lessons learned from ASCAP to both inform the overall concept of operations. How do we operate this telescope? And yeah, the current plan is not to have operators, but to have people in roles that contribute. So think of it more as remote management rather than remote control. And then develop also a scheduler similar to Sauron, but better in every way. So that's, and feedback some of that knowledge into CSIRO as well. And that's just a similar kind of high level overview. So some of the challenges and mitigations that we've had to deal with. So this is a very new and different approach. The science community is still, I think, coming to terms with, dynamic scheduling is one thing, but reactive and that sort of thing. So what we've tried to do here is just demonstrate based on delivery. So the efficiency, delivering data products, and also trying to improve understanding. And I guess if you have more questions or things we could do, that would be great to hear. Scheduling efficiency, like I said, is affected by downstream issues, but the visible thing to users is the telescope isn't observing. So how do you communicate what the actual reasons for those inefficiencies are, and how do you track them across a very complex system? So we are improving the reporting there. Ability to predict the future. So I think that has actually been something quite challenging. It's, I guess, where astronomy starts to go into astrology again. But on the high level timelines, what we're doing is coming up with high level targets, things, forecasts. These actually end up constraining our observations because we said in this month we will do these things. This month changes, but we're still like, do we do these things? Do we do the things we could do better? So that's still a work in progress. And also just distinguishing between the limitations of constraints. I want to observe for 14 hours, but I want to observe at night, and night is 9 hours long. So that sort of thing where it's not really scheduling, but it's the constraint. Okay, so to quickly go, so that's the detailed one. To go through some of the other ones very quickly. Automated workflows, science-ready data products. I know this is something a lot of people are thinking about, and scheduling is just one piece of the overall operational workflow. This, again, doesn't necessarily apply to all facilities, but it is something as a community we're moving towards. And so ASCAP is designed to be a demonstration of science-ready data products to the community. The idea is astronomers provide science requirements and they receive data. And so in between, the observatory really leads everything else. So some of the challenges we've seen with this, there's limited precedence. This is something different observatories do to different extents. And so we've really had to, I guess, it's quite ambitious compared to the model of astronomers get their data, they work on their data, eventually they publish it. And so there's been a lot of working with the community to, I guess, optimize the new approaches and build strategies, but that has taken longer. But I think it is going in a good direction. The efficiency of the overall ecosystem is something that starts lower and improves over time. Again, look to improve, learn from lessons of the current systems and improve for future. And then we also have the evolving role of astronomers over time, which sort of links back a little bit to the AI question. And so if you're interested in that, then I can recommend the ADAS proceeding from 2019. Collaborative intelligence. So how do we work with automation? How do we work with AI? In CSIRO, we had a future science platform called Syntel. And one of the greatest things about it was multidisciplinary. So rather than just working with, astronomy parts of CSIRO, we're also working with Data 61, which is our data-driven part. We were working with mineral resources or cybersecurity. And so the Syntel project was really focusing on using the complex system data we have, trying to detect outliers better, have error mitigation, as well as using our raw data. And this is ongoing work in collaborating with Data 61 to both continue to develop the tools, but also improve the brokerage of all the information we produce. This is Ben's, I think the main point of showing this is that ASCAP is complex. There's a lot of different inputs. There's a lot of different sources of information. And this is Ben, one of our postdocs, attempt to summarize the ASCAP system. And because Ben is building, so they're building a kind of like the brokerage, thinking about how do we bring all this information together and make good decisions. These are some of the examples of the projects. So the three kind of areas have been outlier detection for hardware data, because we have a lot of it. We also have outlier detection on the raw data. So things wrong with antennas, can we react to that faster? As well as the kind of, I guess, more where it starts to overlap with social science. How do we build these things to bring this information together? And what role do automated processes or a broker agent play compared to the human expert or the human less expert and that sort of thing? So those are some of the things. What we've found in this project is that the fuzzy boundary, the space between, like it's easy to build an AI in some sense, and it's easy to have a human do something. When you try to make them work together, you try to define collaborative approaches. That's where it's a research area. And so I think we've really benefited from, especially working with people outside of, and that comes back later, but working with people outside of our subject matter area, because there's, it is really a multidisciplinary thing. Synthesizing information, it took a long time working with people outside of ASCAP and outside of astronomy for them to understand what ASCAP is, the context, the system. And so I think, yeah, that's really kind of emphasized the importance of translating beyond the specific context. Still a work in progress, but that has been something that we have seen. Like I said, the multidisciplinary. We've also seen changes in the research landscape. So structures that existed before don't necessarily exist again. So how do you keep certain things going in those changes? And so I think there's a need for this broader strategic support and thinking about how some of the big challenges in the future we're facing are going to have to be beyond astronomy, beyond radio science, beyond even just science, and we have to work with other areas to solve them. And so the last one is distributed collaboration. So as much as I love automation and as much as we try to do as much as we can without relying on human intervention, we do still have a really important human element, both for collaborating to run a telescope, but also for operational visibility. So using tools and technologies to try to understand what the system is doing. Teams are increasingly distributed. That's not going to go away. And we're actually a microcosm for the broader future of work, which is going to be national, if not international, forever. And so both ASCAP and DSA, which are the two key case studies here, really rely on effective distributed collaboration, not even just, Australia, US, but even within California, between Pasadena, between Ovro, eventually between Spring Valley. So this is the future, and we have to think about interesting ways to solve it. So some of the ones I want to highlight here. So with, I don't know if Kevin will be surprised to see the monorepo up there, but I actually feel like that's been really good. So what this has been is, so it's one repo where everyone's code for DSA is supposed to go into, which is always, I feel like, a dream in collaborations on software. But it's actually been really good because there's been a lot of nice processes and support to help make it happen, but it also has increased the visibility of software code across the project. And everything is issues and, there's collaboration there. So that's been really good, I think, as a software example. But other things are things like VR or hybrid. And if you're interested in that, I'll probably bring my headset tomorrow and happy to talk to you more about that. So some of the challenges, live versus asynchronous. This could also apply to in-person versus online. So you have to choose the right mode. Technology in specific contexts. We've had the problem with ASCAP with radio quiet. We can't exactly just send drones out everywhere. So there are certain specific radio astronomy problems to solve. And so you need multimodal. Like on site at ASCAP, we have to use phones some of the time, or we have to have people be inside the shielded building to be able to communicate via internet. Asynchronous communication, so that's been really important in DSA, but also even just Perth Sydney is sometimes asynchronous. So the fact that we do have these communication channels available has been really critical, and there are no solutions to the impact of human preferences, but I'm happy to discuss it with you. So, so those are some of the examples. Like I said, I'm really keen to hear from people about both examples of automation, as well as if you're interested in any of these in terms of how we think about the future. So I encourage everyone to consider for your projects that you're working on the upgrades to come, think about how autonomy may be part of that and how it may help things be more efficient. We should collaborate more. That's always the thing. So yes, so please get in touch and I'm happy to chat throughout the week. And not everything needs to be AI. I think we all know this. Not everything needs to be an LLM. LLMs are great in some senses. Really good for when you have a knee injury and you want to understand what your surgical options are. But, there are certain cases, and sometimes actually just a really good automated script is much better than an AI. So yeah, that's everything. Thank you.
So we have time for a question or two.
So with Sauron, it seems like the projects have the least constraints that they're observing for a lot of time.
Yeah.
How it pans out.
It would be great if we could, because that's sort of like, the way you reward these AI systems, right? Is like least constraints, they get more time. In practice, we're committed to delivering data for all the teams in certain amounts. So even if a team is highly constrained, then we still sort of have to solve it somehow. So I think we have been tried to be like the least constraining you can be, the better. And we try to be clear about what constraints are worse than others. But ultimately, they've been all assigned this X number of hours. So even if they can only be observed like a quarter of the time as opposed to 75% of the time, we still have to figure out, well, how do we do this? So that's, yeah, but it would be good to have that for future facilities. Definitely, it should be.
Thanks. Any last question before we go to the paper? If not, then thanks, Vanessa.
Take your time. Thank you so much.
I'm glad you're here.
Yeah.
So you can see that screen. This works, and you'll have to use the
Use this. Okay, sounds good. Okay. Well, hi everyone. First, before starting, I need to apologize and to thank. So I went out for dinner yesterday and got the worst food poisoning that I've ever had in my life. So I couldn't make it this morning. And the acknowledgement, thank you so much for to the organizers for this last minute change. And sorry for keeping you up here at 5:30 p.m. It's already 2 a.m. in Canada. So yeah, my name is Pedro Villalba González. My pronouns are he, him, and I come from the University of British Columbia. I'm a second year PhD student, and today I'm going to talk about the Canadian Galactic Emission Mapper. This is a new instrument we are in the process of building, commissioning, and almost data analyzing now. And despite the name, we have a cosmological goal that I'm going to try to convey for the first half of the talk, and then I'll get into what we are up to right now, what the status is, and show a couple very, very preliminary results. So first, as I said, we do cosmology. Questions such as the age, the composition of the universe, what the ultimate fate of the universe is, are things that humans have been asking themselves for a while. We are entering now a era of precision cosmology in which many of the answers to these questions we know to a huge degree almost to a percent level. We know that dark matter makes up to 27% of the universe, dark energy makes 68% of the universe, baryonic matter is just about 4 or 5%. We know that the universe is expanding. We know that this expansion is accelerating, and much of this we know from observations of the cosmic microwave background. This is the image that the Planck satellite took of the cosmic microwave background. Well, this is actually the anisotropies of the cosmic microwave background. This the CMB, as I refer to it from now on, is this light that fills the entire universe. It was emitted when the universe was a redshift of 1100. So when the universe was 300,000 years old, just a really baby picture of the universe that we are fortunate enough to be able to measure. And it's super homogeneous. It's homogeneous in almost apart in 1 in 100,000. And these are these very tiny fluctuations that exist there. And just note how the color varies in the range of micro Kelvin, whereas the CMB is just 3 Kelvin. So we have this radiation filling the entire, the whole universe, and as I said, much of the cosmological information that we have right now, we know from observations of the CMB. One thing that is quite shocking about this is how uniform the CMB is. If we were to look back on time, points that are farther away from each other for more than half a degree were supposed to not be in causal contact with each other. So there is not really a it doesn't, at first one could think, oh, like how come they are so homogeneous if they were never really in this thermodynamical contact. This is called the horizon problem, and cosmologists came up with a solution to this something like 40 years ago. That was the suggestion of this process called inflation that happened just when the universe was a tiny fraction of a second old, something like 10 to the minus 34 seconds old. And if this had happened, the gravitational waves that would have been sourced just when the universe was, as I said, a tiny fraction of seconds old, could have left an imprint on the cosmic microwave background. This imprint would have been left in the polarization field of the cosmic microwave background. What I showed before is the intensity of the CMB, but turns out that the CMB is also polarized, and we have been able to measure the polarization. We were able to do that 25 years ago. The way that in cosmology, we look at the polarization of the cosmic wave background is not in terms of X and Y. We do this other decomposition called an E and B mode, something like a divergence-less and a curl-less pattern, just as these images that I'm showing here. And turns out we can decompose. This is just another decomposition that we can do of any polarization field. Scalar perturbations could only source E modes, and these E modes we've already been able to measure. And then we have tensor perturbations, which are these primordial gravitational waves that I was talking about before, that could source both E and B modes. I would say we don't have direct evidence of inflation yet. So finding these B modes will be something I have written here the best evidence that we could have of inflation. There are some other people that say that is the holy grail of inflation or smoking and evidence of inflation, but there are always a lot of theories that are there to fight against those words. The charm about potentially finding these B modes is that depending on what the magnitude of these B modes are, we could be able to distinguish between the whole slew of inflationary theories that exist. And these inflationary theories are distinguished by this tensor to scalar ratio, this R parameter that basically inform us of what the ratio between B and E modes in the CMB is. Okay, this polarization field of the CMB, as I said, we've been able to measure. It was something that cost a lot of time and effort, and it's a really challenging process. There are many reasons why this is challenging. One of them, and the one that I think we can more easily solve, is the fact that between us and the CMB, and again, the CMB is the oldest light in the universe, so the farthest light away from us, is that we have foregrounds. And anything that, for cosmologists, anything that is not the CMB is a foreground. Being the first and almost most important foreground for us, our own Milky Way, the galaxy that we live in. This radiation emitted from the Milky Way is multi-component and is polarized. The polarization can have a spatially dependent spectrum, what makes it even more challenging. And some of these components are more strongly polarized than the CMB, depending on what frequency we are looking at it. And again, as I said, the CMB is polarized and the polarization is very faint. Just to give an overview on what the status of these foreground observations are, around 70 to 100 gigahertz. That's what we call the cosmic wave, the CMB observing frequency. if we look at intensity here, we see how even the foregrounds in intensity are way more multi-component than in polarization. The CMB is still dominates there. It's still brighter. Whereas in polarization, it never is. The synchrotron radiation from the Milky Way, the thermal dust, and a potential anomalous emission here are always above the CMB. So not only we have the issue that this is a multi-component problem, but also that that the CMB never dominates over this frequency. Observations here, these are all the bands that the Planck satellite cover. This is, I would say, at 23 gigahertz, the best estimation that we have of how polarized synchrotron looks like in smaller, smaller frequencies. And even this map was obtained with an instrument, with WMAP, with an instrument that was not designed at all to measure polarization. The main goal of WMAP was a different one. This is kind of like a gift that came from that instrument. And just to give a last example of how messy this polarized foreground estimation is, these are two maps that, even though these are two maps in the same scale, that even though it looks like they are measuring completely different things, are two estimations of this spectral index of synchrotron radiation. On the left is the Quixote 11 and 13 gigahertz data with WMAP and Planck, and here is the just the 1.4 and 2.3 from SPAS 1.4. I'm not remember from where, plus WMAP data. So quite a hard measurement, and a measurement that right now we don't have an estimation in the literature of reliable estimation, I would say, in the literature of what the actual spectral index of synchrotron is. So to try and shed some light here, we've been designing for the past 5 years. We've been building and designing a new instrument called the Canadian Galactic Emission Mapper, CGEM, which is just a 4-meter on-axis telescope located at the Dominion Radioastrophysical Observatory, and I'll show a picture in a bit of where that is. This is just in northern British Columbia in Canada, in the west coast of Canada. This is a picture we took a couple months ago of the instrument, and the main goal that it has is to map the northern sky in 8 to 10 gigahertz with a spectral resolution of 1 megahertz at 0.5 degree angular resolution, just with the goal of being able to get very high signal to noise maps of galactic synchrotron radiation, so that we can use them as a template for in the removal of these galactic foregrounds for CMB, for cosmology experiments. The fact that we are measuring at 8 to 10 gigahertz, which was where synchrotron radiation is way brighter than is way brighter than at 100 gigahertz, makes it so that we just need a target sensitivity at 10 gigahertz of 25 to 100 microkelvin, way more achievable than the 30 nanokelvin resolution that we will need, sensitivity that we will need to be able to be useful for experiments such as BICEP or in the South Pole. So the side, that's just here, interior BC, so a 16-hour long flight plus a 5-hour car drive from Vancouver, which makes it a very accessible site for us. We can just drive for an afternoon and get to the observatory, making it quite easy for us to reach there, but of course super far away from the beautiful Sydney where we are all today. As I said, we just want to make a map of the northern sky at 8 to 10 gigahertz. So the scan strategy that we have is the most straightforward scan strategy that you can think of. You just point your telescope at a constant elevation and you move. We are right now moving at constant speed, but we'll switch to a variable speed scan so that we can create an equal area coverage. And the charm of doing this, of having this scan strategy, is the fact that if we point at 41 degrees in elevation, we are always going through the north celestial pole in our scan, which makes it way easier to do later this striping and data processing of our instrument. And these are just some plots of how low we could go in elevation. We are designed to go to be able to scan from 30 degrees to 55 degrees. So we could even get to -5 and have a bit of south coverage, since that's when ultimately these kind of experiments are more, these results will be more useful. I'll quickly go over what the signal chain, how the signal chain looks like. So first we have an antenna, then we have an orthomode transducer that will split our radiation into right circular polarization and left circular polarization. Then we'll go through an analog radiometer and we'll process to digitize it in an RFSoC 4x2. And the charm again that we have and something that we've kept in mind through the whole design of the instrument, is to put the polarization in the crosses instead of the autos, so that we can get rid of the noise bias. And even though that means that we have worse maps of T, at the end of the day, what we care about is Q and U. So it's the whole charm and the whole thought that we've kept in mind through the whole design of this instrument is polarization purity, and making sure that our instrument was just exclusively designed with this goal of trying to get the best Q and U maps. So the antenna that we have, that I showed the picture before, this is the last optical design. This was designed by my lab mate Josh, who gave a talk 2 years ago, and also at URSI in Japan. We just have a 4-meter on-axis design, which is this. Our primary mirror is a Gregorian mirror, and then we have a secondary mirror with this small hard feed, and then we have a circular waveguide, and right after that we have an OMT that sits yes, right there. This is the reality of the instrument. This was the deployment in February. So here you can see how you have our primary mirror, the secondary mirror, which is hidden here with a radome that supports it, and then we have the horn aperture, have a horn and an OMT right below. Right after this antenna, we have our analog radiometer. We are supposed to have a cold and a warm stage, basically a cold stage amplification where we will have our LNAs, and a warm stage amplification. Right now, we only have warm LNAs, so all the results that I'm gonna show are just with warm LNAs. So that just means that we haven't installed our cryo yet. We'll proceed to that later. But the whole idea of the radiometer is very straightforward. It's a super heterodyne receiver that down converts from 9 to 10 gigahertz to 0 to 2 gigahertz. We have a common LO, mixer, low pass filter, IF amp, and then the signal gets digitized in as I said before, in a RFSoC 4x2, and giving us a spectral resolution of 1 megahertz. This is the reality of the receiver. These are pictures we took a couple of years ago when we were testing this in the lab. We'll have monitoring of the LO, current, other housekeeping products, and this is just how almost compact the radiometer. Oh, here, how compact the radiometer post RNAs look like. this has been an overview of the instrument. As I said, we have a warm system. And this year we started taking data in March, April, and this is the first sky map that we were able to get. This is a map of the autocorrelation. And just to note, this is a map with very, very poor data processing. This is just a chi-square field with no attempt to correct for anything else. We are busy trying to figure out 100 other things that are wrong with the instrument before. And this is just data taken over one night, the night of May 1st, and just to show, like even with one night of observations, we are able to see Casey, Seagate, the galactic plane, and we have a bunch of other, as I said, instrumental issues, but this is the very most preliminary result that we've been able to get. In terms of status, and I'll finish the talk with this, we were able to get CGEM working in early 2025. We have been working on this project since 2021, September 2021. We need to improve the thermal control of the electronics and the azimuth encoder. One thing I didn't mention is the map that I showed before was made without controlling temperature of anything. We just have a black box in the middle of just behind the telescope, and no matter what the temperature outside it is, the box just fluctuates with that. So there are huge gain drifts, there are a huge whole bunch of issues by just not doing that. So we'll do that this summer, and as soon as I'm back to Vancouver, that's the part that I have to be working on. We'll also collect housekeeping data. Right now, we are not even collecting temperatures. The only temperature that we have is the dye temperature in the RFSOC. We don't have currents. We don't even have accelerometers in the mount. The only thing we have is an azimuth encoder. So we'll be working on that this summer. Then early next year, we will deploy the cold radiometer. We have the cryo already in the lab, and we are starting testing of the LNAs. And if things progress as we hope that they do, by late 2026, early 2027, we'll attempt to deploy a copy of CGEM in the southern hemisphere, probably in Chile. So we don't need to change CGEM. It will be Chilean galactic emission mapper. And where we will actually be more useful for the current search of B modes, since there are no such experiments in the northern sky. And with that, that's the end. Thank you.
Questions? All questioned up.
Is there a switch, a sticky switch, or any kind of, how do you control the red noise?
How do we control, sorry?
The red noise of your amplifier.
Oh, right now we don't even control it. Right now our 1/f knee is 1 Hertz. So what we are attempting to do is just make it thermally stable, and that should just keep it to a 0.1 Kelvin, which is quite easy to do, especially for the LNAs, and we hope that should be enough. We just need to control it to 20 seconds. Our scan period is 20 seconds, so as long as the red noise is not.
Anyone else? Going. All right, thanks all, and we'll see you again tomorrow.
Thanks
again.
Thank you.